Hello, one and all. I am Dr. Abir Ghosh, and I truly appreciate this opportunity to present before the multiscale modeling community. I would like to present one of our very recent research work at Imperial entitled as a shrinking core model for the degradation of nickel-rich NMC electrodes. We are focusing on specifically NMC 811 electrodes. In this presentation, I will focus on the effect of positive electrode degradation in the lithium-ion battery operation and how the developed model is going to account for the same. Before going to the details of the developed model, let's get an overview of NMC electrodes and their importance in lithium-ion batteries. And also we will look at the specific issues of these electrodes that needs to be addressed to improve the overall performance of lithium-ion batteries. Lithium-ion batteries still remain a very good choice for electric vehicles because of their lightweights, compact design, and high specific energy. They are also used for grid-scale energy storage applications as well. However, the main obstacles are the cost and the lifetime of these batteries. Currently, battery manufacturers lack information about the aging of lithium-ion batteries at different climate and operating conditions. So degradation studies are important, and specifically degradation of positive electrode are still at a very novice stage. Let's take an example of an electric vehicles with a driving range of 300 miles. And for that, one needs a battery, lithium ion batteries with specific energy of 750 watt hour per kg. So that means around 200 milliamp hour per gram for each electrode if each electrode operates at an average of 3.8 voltage. Now let's look at the electrode choices that we have. Now regarding the negative electrode, the graphite electrodes have been used traditionally and they have an specific capacity, theoretical capacity of 372 milliamp hour per gram. However, there are several choices for positive electrodes are available, and recently it has been observed that NMC electrodes have a theoretical capacity of 275 milliamp hour per gram, which is as high as it gets for any positive electrodes that we have currently in the market. However, uh, the reversible capacity of the NMC electrodes, especially for the nickel-rich NMCs, are around 190 milliamp hour per gram. Now, we cannot, now this the reduction in the reversible capacity is because we cannot extract all of the lithium that are present in the NMC electrode. Now, why is that so? Now, what are the reasons why all the lithiums cannot be extracted from the NMCs? So one of the reasons are the NMC electrodes are unstable at higher SOCs. Okay, so basically at higher degrees of delithiation, NMC electrodes goes for an structural reconstruction. Now, what is the structural reconstructions of NMC electrodes? As we have mentioned in the previous slides, whenever the lithium ion content in these electrodes are very low, the transition metal layer of these electrodes goes through a phase change. So the layered transition metal layers of NMC electrodes goes through a phase change to produce spinel and rock salt layer, and these layers are disordered in nature. However, this phase transition is thermodynamically more favored, and the produced passivation layer also hinder the lithium ion pathways within the electrodes, and that gives rises to the power fade of the batteries. Not only the power fade, during the phase transition, there is a release of nascent oxygen related in each steps of these phase transitions, and these nascent oxygens are much more reactive in nature. So they either produce oxygen gas just after diffusing out from the solid positive electrode phase, or react with the ethylene carbonate of the electrolyte to produce carbon dioxide and carbon monoxide. The gases produced, like oxygen, carbon dioxide, and carbon monoxides, are dangerous for the battery health. Experimentally, the passivation layer formation and oxygen evolution has been observed whenever the NMC electrodes has been cycled around 4 volt. And this passivation layer formation and oxygen evolution has an effect both in the capacity fade and impedance rise. As mentioned in the previous slides, here comes the experimental evidence of there is a decay in the specific capacity of NMC electrodes, and also it is related with the increase in the oxygen release or the evolution of the oxygen whenever these electrodes have been cycled at around 4 volt or higher. Now, to have to understand this phenomena or to model it, so both the thermodynamics and kinetic understanding is required, and also it is a multi-scale problem. So a lot of molecular level information is also must to model this phenomena. At the same point of time, we need to develop a continuum scale model to include or to study the kinetics and see that from there can we measure or can we have a look of how much amount of capacity fade is happening because of this phenomenon. So in this presentation today and in this research work, we have focused on developing this continuum scale model and to include the kinetics and see that what are the parameters those are affecting the capacity fade due to this degradation mechanism.